So in the general framework, um, the test statistic is used because we know what its distribution is. And that means we are able to proceed with determining probabilities for what we see in our data. So this table I put together is going to go over these single mean test and the single proportion test. In the single mean test, there's two situations where we know what the standard deviation sigma is, and this is actually very rare. It can happen when you have like a national registry with millions and millions of data points, and that doesn't change much over time. Then you can maybe know what sigma is. What's much more the case is that we have a single mean test and we have an unknown sigma. So we don't know what the standard deviation in the population is. The requirements for using this test is none, and that's governed by the student's t distribution with degrees of freedom given by n minus 1, n being the sample size that you have. If you do know sigma, then it just follows a standard normal distribution. And we would use the standard error in the previous formula, the one I told you we generally look up. We would use sigma over the square root of n because we know sigma. If we don't know sigma, then we're going to just substitute it with the sample standard deviation divided by the square root of n. And this is the standard error that we'll be using for most of our single mean tests. In Excel, there's three different functions that we can use to look this up. If our test statistic is less than 0, and we know we are dealing with a left-tailed test, we would expect, so imagine that that's actually a normal distribution around 0. Okay, this test statistic is going to give us, when we put in our test statistic value, it gives us the probability in the left tail. Okay, the t distribution for the right tail we can get using the previous function, just subtracting 1 from it, but it's going to automatically, Excel will go ahead and give you that right tail distribution. Again, in this case, we have a test statistic that's positive, so it's greater than 0, and we want the value, the amount of probability that's out here in the tail above that test statistic. And that's obtained using the function tdist.rt. Notice that in the test distribution function, you have to put in the value, the degrees of freedom, and true for cumulative. But in the tdist right tail test, distribution, you're only going to have to put the test statistic and the degrees of freedom. It automatically assumes that what you want is the entire probability under that tail. And then for the two-tailed test, and I'm going to be talking about, reminding you more about these scenarios in a second. But in the two-tailed test, when you put in the test statistic, whether it's positive or negative, so if it's positive or a negative value, so I'll denote that with negative of the absolute value of the test statistic. The tdist2t test in Excel gives you the sum of the probabilities in both tails, so it adds them up. So it's giving you both of these. And then for a single proportion test, if we have a relatively large sample, so we need about 30 or more points in our data, and we can satisfy that the n, the sample size, times the observed proportion is greater than or equal to 5, and that n times 1 minus an observed proportion is greater than or equal to 5, Then we can create the test statistic, and it follows a standard normal distribution. So normal.s.dist, we put in the test statistic and we put in true. And again, the reason for true, if you haven't used this before, is because if you put in false, it just gives you the height on a normal distribution curve, and like the y coordinate. So like, let's say this is the test statistic down here. We put in the x value basically, and it's going to give us the y coordinate. And if it says false, but if it says true, it's going to actually give us all the probability always to the left. So this is where we have to really we don't have the luxury of having these three different tests. For the normal distribution, we just have the normal distribution to the left. So the standard error formula is rho naught times 1 minus rho naught. Again, the rho naught is that generally agreed upon value for what the proportion is expected to be that we are testing against. And so it's rho naught times 1 minus rho naught divided by the sample size and then the square root of that whole ratio. The next step for the general framework for hypothesis testing is that in all hypothesis tests, you need to determine if your test is left-tailed, right-tailed, or two-tailed. And in order to do that, you focus in on the alternative hypothesis. So the H sub A. And this is just a breakdown of the single mean or the single proportion alternatives for comparing them to a number. So if the alternative is that the population average, the mu, is less than some number mu naught, or if you're doing a categorical variable where you're looking at a proportion, and the alternative is that the proportion is less than some value, then this is left-tailed. This is a left-tailed test because the parameter is less than the value. On the other hand, if you are testing your alternative, you want to see if your value is greater than some established number by the average or the proportion. This is a right tail test. And there's also the situation where your alternative is that they're just different. You're not claiming that one is that it's greater than that number or less than that number. You just want to know if it's different than the number. So in this case, it's the population mean or the population proportion being not equal to some value. So once you've identified which tail your test is, and you calculate the test statistic, you get like an automatic like secondary check on whether it's left-tailed, right-tailed, or two-tailed. Well, actually left-tailed or right-tailed. If it's two-tailed, you just have to know that that goes with the not equal to symbol. But if it's left-tailed or right-tailed, when you calculate your test statistic, you're going to use that to determine the p-value, which is the probability of seeing the test statistic value if the null hypothesis is true. And this is the probability in the tails. So as I was saying, the secondary kind of test you have to know you correctly stated if it was left-tailed or right-tailed is the test statistic. Well, if it's a left-tailed test, should be a negative number. It'll be to the left of the 0 mark in the middle of the distribution. If it's a right-tailed test, that test statistic will be a positive number. And if it's neither, we're not sure what side it'll land on, but if it's positive, you put the number on the right and you put the other, or if it's on negative, you just put the number and it's negative on the distribution. And then what we're going to do is determine for a left-tailed test the amount of probability or area under that tail of the distribution. That's the p-value. Remember, in these probability distributions, it's the area under the curve that is analogous to the amount of probability. So we have a little bit of probability out here, and we have a little bit of probability out here. And this is a right tail test, so it's the amount of probability in the right tail. And if it's a a two-tailed test, then we have to add the probability that's in both tails. even though our test statistic is only one of these sides, we're still on a two-tailed test going to add the probability from both tails. And I just want to remind you that on the previous slide, I had shown you that for a single mean test with an unknown sigma, you are able to use a different function in Excel for each one of those tests. So if it's a left-tailed test, you use t-dist. If it's a right-tailed test, you can directly put in the test statistic and the degrees of freedom and get the right-tailed. And if it's a two-tailed test, you can use the t.dist.2t and get the two-tailed probability in the tails. The next thing that we're going to do after we get the p-value in every single hypothesis test is you're going to compare the p-value to the significance level alpha. So in a sense, the p-value is telling you what is the probability that you would see what you're seeing if the null is true. And alpha is saying, well, this is the probability that we're willing to be wrong. So if your p-value, and this is actually the hypothesis, this is everything prior to this was setting it up. At this point, you are now going to conduct the test because you compare the p-value to the alpha, and you decide if you're going to reject the null hypothesis or not. So if the p-value is less than alpha, you do reject the null and you accept the alternative. The test is statistically significant. If the p-value is greater than or equal to the alpha, you do not reject the null. The test is not statistically significant. And you would say something along the lines of the data does not support rejecting blank, 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 whatever the null hypothesis is. The idea here is if the p-value is less than alpha, so what we're saying is this is the probability that we're willing to reject the null, even if it's true. This is the risk we're willing to take. So if we see anything with this kind of amount of probability, we're okay with it. So the probability out here, if the p-value is less than that risk level, we're like, okay, the probability of what we're seeing is so low that we believe that the null just cannot be true, and we're within the risk level of being wrong. So we are willing to reject the null at that point. And we know that the chances of being wrong are less than the alpha. On the other hand, if the p-value is greater than the alpha, as I sketched over here in this one, that means the probability that we're seeing has a higher probability of happening than what we're willing to accept as a risk of being wrong. So we will not reject the null hypothesis in that situation. And in the two-tailed test, you add the p-values from each tail together and compare them to the alpha. Another way to think about it is you split the alpha in two and put it in each tail. I don't want to confuse anyone there. Just add the p-value by adding the probability from each tail together and then compare that to alpha. And just follow this rule right here. If the p-value is less than alpha, you reject H0. Now that we've gone over the general framework for running a hypothesis test, I want to return back to the two examples that we did when we have two groups or two subpopulations that we want to test some quantity in. So the first one that I gave you an example for was when you have a difference between two means. And in this example, we wanted to ask, is the average spending in 2021 different between male and female organic food superstore customers? So in setting this up or asking this test question, it's really important that we set up two populations. And no one person or one entity can be in both subpopulations. It's okay to leave people out. For example, in example 4, we'll do an example where I show you that. But in this one, we have male and female. Now notice that I am going to be using male and female are the two categories in the variable sex. So you find a variable, a categorical variable that you want to use to divide your population. Note that we binned income into quartiles, and we bin some other variables into quintiles. So those binning values can actually be also used to divide your population. In this case, we're using one that's binary, sex. There's only two values, and we're using all the records in our data set. And we're going to have the two subpopulations, the male and the female. And then the next thing we're going to do is determine we're going to give notation to the parameter for each subpopulation. So in this case, what we're doing is we're saying that mu1 is the average spending in 2021 in subpopulation 1. And then the exact same thing is what we use in subpopulation 2. You have to, these have to be the same thing that you calculate for each, or that you're making a hypothesis for in each of the subpopulations. Because what we want to say is that this thing, which we call mu1 or mu2, is going to be in some ways different based on the membership in one of the subpopulations. So from this, we are going to go ahead and use the test, as I've told you before many times now, is the test is going to go into the alternative. And here we see that we want to know, are they different? So when we use the word different, what we mean mathematically is not the same. Okay, so this is where we're putting in this not the same, is because we're wanting to connect that with the word different. Okay, and then we use the alternative to write the opposite mathematically. So the opposite of not the same is that they're the same or equal. So once we've set this much up, then we're going to rewrite, we're going to subtract the mu2. So let me get rid of some of these annotations. And you'll see that now that we've set this up, we're going to just subtract mu2 from both sides. So mu1 minus mu2 is on the left-hand side, and mu2 minus mu2 is the 0. So what we're going to basically be doing is kind of thinking of this whole side as being a parameter. It's the difference between our two means. And we're going to kind of be treating it the way we first started when we were looking for a single mean hypothesis. So this now has a number on the right-hand side, which is in the notation like the mu naught. Okay, and then we do the same thing in the alternative. We subtract mu2 from both sides, and we say now we want to test if that difference in the means is different from 0. And the fact that it's different from 0 is telling us that it's a two-sided test. And for this one, we're going to go with a significance level of 20%. We're willing to accept a little more risk because whatever we end up doing is based on average spending. And we're not really sure if average spending is the primary endpoint, although it's starting to appear that way. And so now when we get the test statistic, it's going to be exactly the same as it was before. It's the observed minus the expected over the standard error. Now the observed, this notation we haven't discussed yet, but it's the sample mean from the first sample, where we divide our sample into these two subpopulation definitions. So we're going to take our sample data and we're going to divide it into the male and female customers. And we're going to get a sample mean from each one of those subgroups. And we'll take the difference in them. That's the observed data. So the observed data, this is coming from the sample. And it's going to be this difference here from each subgroup. And the expected is the right-hand side of the null. All right, this is where this expected comes from. So it's always the observed minus the expected. So the expectation is that the difference in the means will be 0. And what we're going to do is compare that with the observed difference in the means. And since the 0 just drops out mathematically, it just is the sample difference in the sample means divided by the standard error. And the final example that we did was looking at the difference between two proportions. And in here, the question was, or the test that we want to ask is, do gold customers have a higher proportion of very satisfied than bronze customers? So what you need to understand is, first of all, what are the two subpopulations being defined here? The first subpopulation is the gold membership organic food superstore customers, and the second one is the bronze. And we want to test the same thing in both of these. We want to test the proportion of very satisfied. Now, proportion is just one category value within the categorical variable of satisfaction. And that's how you have to develop hypothesis tests when you have categorical variables. You have to pick one of the category values, and you actually can bin 2 or 3 of them together and come up with a proportion for that variable that you want to test in the 2 separate groups. So in this case, we're going to let row 1 be the population proportion of very satisfied in subpopulation 1. And we're going to have the exact same thing, right? These have to be the same thing in order for this to even be possible to make sense from a logical point of view. We have to check the same quantity in the 2 subpopulations. And we just give the quantities a different subscript to identify them. So we're going to state, going back to the question, is test, do gold customers have a higher proportion? So right here we have this word higher. And that means that we are asking, is row 1 greater than row 2? This term right here, greater than, is coming from higher. Okay, so do the gold customers have a higher proportion of very satisfied? And then we're just going to use that, right? That was building the alternative. And then we're going to use the opposite mathematically to go from greater than to less than or equal to build the null hypothesis from this. And then we're going to have to rewrite that by pulling row 2 over to the left. So we subtract row 2 here from both sides of this inequality, and that can be rewritten as row 1 minus row 2 is less than or equal to 0. And doing the same thing for the alternative, row 1 minus row 2 is greater than 0. And now that we've converted it to a situation that looks like a single group test, in the sense that we have all our parameters on the left-hand side and we have a number on the right, right? We have this number here. So now that we have a number on the right, we can use this inequality, and it's telling us that we're having a right-sided test here, because this alternative hypothesis is greater than 0, or on the right side of the number. And then we need to state a risk level. So our significance level that we're willing to have a type 1 error is 10%. And then we're going to come up with a test statistic like we do in every case. And in this case, it's going to be the difference of the observed minus the expected. Sorry, I shouldn't say in this case. In every case, it's always the observed. So this is the observed data right here. And it's the P bar is the proportion in the subgroup of our sample that are the gold customers that and we want to get the very satisfied in the gold customers in our sample. So this is the observed. This is coming from the sample data minus the sample data that are the bronze customers, and we're going to get the proportion that are very satisfied there. Notice there were silver customers and a few that were not in any of the membership categories, and they are excluded from our sample data that we're using to run this test. And that can happen, and that's okay. Right, so then we're going to subtract off from the null the expected value. So the difference in the proportions from the null is no greater than 0. So it's less than or equal to 0. So we're doing a right-sided test, and we're going to use that upper bound. That number here is our observed value that goes into the test statistic. But it's just 0, so it can be dropped off. So we can just rewrite the numerator as the difference in the sample means that are observed. And just like everything up till now, we're dividing by the standard error, and that's where we are going to look that up, because those tend to be more complicated formulas. So the standard errors for the difference between two means, I put in this table, and I put a little bit more information. So we have the difference between two means, and we have 3 cases. One is where we assume that they're equal and known. And in this case, you can use the standard normal distribution for that. And there is a setup kind of interface in the data analysis tool pack in Excel that lets you do this. It's called the z-test, the 2 sample for means. And then in the more common scenario where we don't know the sigma, the standard deviation, but we can assume that they're equal, so we have a reason to believe that they're equal, then we can use the student's t-distribution, and that is done with the degrees of freedom n1 plus n2 minus 2. N1 and N2 here, of course, being the sample sizes for each subgroup. So we take our sample data and we divide it into subgroups, and we have to get the sample size for each subgroup. There is an easier way. So in this case, the standard error is pretty complicated. You have to do this pooled standard error. So basically you're saying, well, there's some evidence from the first sample, from the first group, and there's another measure of that sample standard deviation from the second group, and we're going to pull them and then put that together into a standard error. And that's all, you know, once and done kind of thing. You only have to program it once, and so Excel actually programmed it for you. It's again in the data analysis tool pack under the z-test 2 sample, assuming equal variances. And the third situation is if you have a difference between 2 means, but you do not assume that the standard deviations are equal. In this case, we can use the student's t-distribution, but the degrees of freedom are much more complicated. The calculation for them, it's called the Welch's degrees of freedom. And this gets usually rounded down to the whole number lowest. Excel does not do that. Excel just rounds, and we're just going to accept that for our purposes. And that enables us to use the data analysis tool pack that has the z-test 2 sample, assuming unequal variances. And that's fine. This is theoretically the one that's usually preferred, but there are some software packages, Excel being an example, that rounds a little different than what we normally would do. The standard error formula that is embedded inside this little program is the variance, the sample variances divided by the sample sizes and added together like so, weighted by their individual sample sizes. And then the square root of that whole thing. Okay, the next one that we're going to need is a difference between two proportions. And the requirements for doing this test is that the sample size for the subgroup 1 times its proportion, sample proportion, is greater than or equal to 5. And the same thing holds for the second group. If that's the case, then the test statistic will follow the standard normal distribution. Since there is no actual test in the data analytics, data analysis tool pack, you have to run this by hand. So we actually have to program the standard error, which is a little complicated. I will go ahead and program that and upload a file to Brightspace that has this programmed in, so you can use the standard error formula and use that to obtain your test statistic, which would then go into the Excel function for a normal distribution. And just to remind you, if you have to do a right tail test, because this is the function we have, and this always gives you the probability to the left of this test statistic. If you want to know the probability on a right tail test, you have to do 1 minus what you get from this. Okay. So this is just a quick overview of the 6 steps that we've been discussing. This is from 210. All this material really is from 210. Just reviewing what you've already done before. One thing that you may or may not use very often is just a description of how weak or strong the evidence is against the null. So if the p-value, so in this case, you don't state an alpha, is basically how this works. You look at your data and you make a statement about how likely the null is to be false and that you can reject it. So if your p-value is greater than 0.1, usually it's considered weak or none. If it's between 0.05 and 0.1, it's moderate. But between 0.01 and 0.05, it's considered strong. And anything less than 0.01 is considered very strong.